Okay, good afternoon everybody, and today is our 11th lecture, what a typical solver for gas dynamics simulations looks like, time step selection and boundaries treatment. So today's lecture will be about practical issues. So previous lectures were about theoretical background for finite volume methods for the numerical solutions of gas dynamic equations, and we discussed a couple of good solvers. We discussed what does it mean, solver. And today I'd like to show you how all these things can be implemented in reality, in computer code. So on previous lectures we discussed the finite volume methods for Euler equations, and so this is the specific, one of the best methods with unique properties, at least, Godunov method. The Godunov method for the numerical solution of Euler equations is based on the exact solution of Riemann problem. So it means that, this is the general formula of our finite volume method. So U is the conservative variables vector, F is numerical flux, and numerical flux is a function of two states, to the left and to the right of discontinuity, and discontinuity in this context, it's a boundary between two neighboring cells, Mn and Mn plus 1. And in the Godunov method, we solve the Riemann problem. We get all these structures, and so it's important for today's lecture. So that is why I'd like to remind you that we solve this Riemann problem and get these wave structures, shock waves or reflection waves, contact discontinuity, and we check. We need to find the region in which the surface between these cells falls in. And then we take these parameters and put them into the flux. And that's the idea of the Godunov method. And we discussed that there are a number of approximate Riemann solvers. For example, one is a current Jackson-Rees flux, or current Jackson-Rees scheme, CRR. And it is based on the analysis of Jacobian matrix, omega R, lambda, omega L. And the idea is that it should be diagonalized, and then we should work with the mod lambda matrix. It's a diagonal matrix with absolute values of eigenvalues on the diagonal of this matrix. And for this solver, we do not need to find all these states, approximate states. We just obtain directly the formula for numerical flux. And for example, the next lecture will be about the multidimensional consideration, multidimensional finite volume method, and we will discuss the issue of how can we generalize our 1D approaches to multi-D, to 2D or 3D. For example, the very convenient thing for this numerical flux is it can be directly generalized in 2D and 3D if we substitute this matrix omega R, lambda, and omega L from 1D to 2D. And so this can be done, in a straightforward manner. And today I will show you how this numerical flux can be implemented in a real program in solver for the solution of gas dynamic problems. And the last lecture was about another approximate Riemann solver. It was we discussed two numerical fluxes, HLL and HLLC, Harten-Lachs-Van Leer and Harten-Lachs-Van Leer contact. And so this HLLC flux, it's a review of this flux, it works pretty well. So it really works, and I can recommend you. So the formula, so this is the general formula of finite volume method, right? And the numerical flux is written in this manner. So we have four parts, and it is based on the construction of approximate states. So we do not solve the Riemann problem exactly. Instead, we say that we have right wave, left wave, and contact wave, and we have two states, U star L and U star R. And actually, again, we need to find the region to which the H of this cell falls in, and we derived all this formula. So if you know parameters to the left and to the right, so UMN and UM plus 1N, it's possible to compute the velocity of the contact wave, if the SR and SL are known, and so we discussed that there are different ways how to choose the velocity for the left wave and for the right wave. So, and if you know this S star, it's possible to compute parameters here, U star L and U star R. So these are formulas. Within the scope of this lecture, E will be used for total energy, not per unit of mass, but per unit of volume. And then if you know these U star states, it's possible to define this F star K fluxes for this case and for this case. So this is an example of an approximate Riemann solver based on constructing an approximate state and then evaluating the physical flux function at this state. And so this is the review of previous lecture. And so this numerical flux indeed is implemented in a lot of solvers, open source software such as OpenFAM and so on and so forth. So and we discussed the main ideas and how can it be constructed. And okay, so that's for review of previous lectures. What are we going to do today? And suppose that we want to solve some practical problem. For example, we want to compute the flow in a shock tube. And we discussed in the first lecture there are typical stages of the process of numerical solution of any problem. So first of all, we should define so it is called the physical statement of the problem. So we at the physical level we should understand what the problem we would like to solve. Then we should define a mathematical model. So we should build the geometry of our object if it's multi-D, also and then we should define the mathematical model. So mathematical model means that we should choose the defining system of equations, partial differential equations in our case. Then we should define and choose the numerical methods, suitable numerical methods. Once again, that's actually very important to realize all these stages, because when you use a sort of black box tool, maybe a number of stages you cannot see them. And maybe you even do not realize the errors that you have at each stage. Then you should implement it in code, and today we are going to discuss how should it look like, how it can be implemented in code, and then simulation results. Shock tube is because we discussed that, for example, SOT's test, SOT shock tube test, I named it in such a manner, is a well-known test for finite volume methods, for numerical methods for the solution of gas dynamic equations, and it mimics the operation of real device. So I took this information from Hansen group. Hansen at Stanford University, it's one of the world's famous well-known groups who study high-speed chemical reactive flows, and they experimentally, and so they do unique experimental techniques to do that. So shock tube it's like a just long tube, several meters long tube with several sections, and it can be used to obtain high pressures. So a shock tube is an impulse reactor that generates shock waves to nearly instantaneously heat a test gas. So it means that there's very fast propagation of the shock wave, and you can obtain almost uniformly compressed and heated mixture. Shock tubes uniquely operate across a wide range of temperatures, so up to 10,000 plus K, and pressures from very low pressure, so you can pump out this gas and get the low pressure, because if you do experiments with chemical reactive media, so usually, and for example, with very high speed flows, the pressures behind the propagating, for example, detonation wave under normal conditions are very high. It's very dangerous. That is why usually people try to work with low pressures and not to get too high pressures behind the combustion wave. Paired with advanced instrumentation, shock tubes can be used to study reactive flows by investigating the physical properties of atoms and molecules and their evolution through time. So usually this shock tube is also accompanied by some experimental techniques how to register the flows. For example, they have the different windows how to record the process. so it is used to discover the new so to get new results in chemical kinetics, fuel design, clean energy. So actually a lot of applications. What is important? A key advantage of the shock tube is its ability to generate a precisely controlled 0D test environment, free from the complications inherent in more complex real-world energy systems, such as engines, turbines, and so on. So what does it mean? So, for example, you want to know how to compute chemical flows with chemical reactions in real devices such as engines, turbines, and so on. How can we do that? For that, we should know how to compute the flows, inert flows, and so our course is about the inert flows. And then we should add information about the chemical kinetics, and this information can be, validated and verified without these difficulties, without these complex flows. And it can be done using these devices like this one. What does it mean? So this is the sketch of the operation of this shock tube. So this is a diaphragm. This is a high pressure chamber, so this is a low pressure chamber or driver section or driven section. And so this is the rupture or opening of the diaphragm. And this is a shock wave. This is the contact surface between the gas that was initially in driver section and driven section. And this shock wave, it propagates towards the closed end. And here we want to measure the properties of our mixture here. And so shock wave propagates and then it reflects. And there's high pressure and temperature region here. And the parameters here are almost uniform. And you can measure, for example, time for up to ignition of a mixture, starting from the moment when shock wave approaches the closed end of the shock tube. And here the parameters are almost uniform. And so here the parameters can be considered as 0D. But actually, for sure, and I also talked about that, the 1D approximation of the process is only an approximation. In fact, you have some multidimensional process of opening of your diaphragm, and there are multidimensional effects. And for sure, your shock wave will not be a planar one. So it will be a planar only at some distance after the diaphragm. The second problem is that we have boundary layers, so the shock wave will propagate, and in reality we'll have the growing boundary layers, and the shock wave will reflect from this boundary, it will interact with boundary layers, and experimentalists know that very often the ignition can occur not here, but near the walls of the shock tube. So there are different difficulties, and so this also about the stage mathematical model. So, for example, we want to simulate the operation of a shock tube, but we can choose different mathematical models for that. We can consider the same process in 3D, in 2D, using viscous effects, or maybe chemical reactions, and so on. But we are going to use the simplest possible model, so just 1D Euler equations. How does a shock tube work? So a shock tube has two main sections, a driver and a driven. Before an experiment, a single-use diaphragm, so this is a diaphragm, is placed between these two sections. The driver section is filled with a low molecule, this one. The driver section is filled with a low molecule weight gas, such as helium, and the driven section is filled with the desired test gas. For example, we want to measure the properties of hydrogen, for example. How can we get the chemical kinetics of hydrogen combustion? We can calibrate it using this data in the shock tube. The driver section pressure is increased until the diaphragm bursts, creating a shock wave that propagates through the driven section. The shock wave heats, compresses, and sets in motion the test gas here. When the incident shock wave reaches the end wall, it reflects back towards the driver end of the shock tube, further compressing, heating, and ultimately stagnating the test gas. So here the velocity of gas is just zero. So it's just the region at rest with high temperature and pressure, and it's very, very fast, high-speed process. That's it. For example, we want to know the parameters of this shock wave to compute it. So mathematical model, for many times we have already written this system of equations. We want to solve just 1D Euler equations, but in contrast to previous consideration, now we have boundaries. So before we did not analyze boundaries, so we just used this picture, one cell, central cell, the cell to the left, to the right, and that's it. And we did not think that actually that can be a boundary here, a physical boundary, for example. We didn't discuss this issue at all. But now we should keep it in mind that so we would like to solve our problem on the interval from 0 to 1, and actually we have some finite time, for example t, the capital, the final time instant. We will use this conservation form of Euler equations, conservative variables vector, flux vector, and the total energy per unit of volume. And for example, we still consider the ideal gas equation of state with the specific heat ratio gamma. And this is not the real problem. So the initial data follows the idea of real problem, but the real problem is the Cauchy problem. So in the real problem, we do not have boundaries. And here we have boundaries, and initial data correspond to some Riemann problem. So at x equals 0.5, we have a discontinuity, and parameters to the right are UR, to the left are UL. And from physical point of view, we want to establish, to impose boundary conditions correspond to a solid wall. They also called non-penetrating or impermeable boundary conditions. So we are going to discuss what does it mean. So from physical point of view, we want to have two walls, left wall and right wall, and we want to solve our Euler equations in this area. So we discussed the problem setting, we discussed the mathematical model, and I also reminded to you that so actually, again, so everything depends on your choice of your mathematical model. So you can consider the same problem, but with using different another mathematical model. Numerical method. To solve this problem, we want to use finite volume solver based on approximate solution of Riemann problem. So it's the Courant-Jackson-Lewis numerical scheme, and we would like to choose this product of matrices. For example, just as 1/2 of this matrix to the left and to the right. So it follows the paper of Holodov. And at the previous lecture, I told to you that actually in 70s, so the people realized that this matrix relates to numerical solution of gas dynamics, and we discussed that there are a lot of different options how to choose this matrix. And for example, so this option works, and so we can use it. And but now we have a number of problems. So the first problem is time step, tau. Up to now, we considered this time step as a constant. And that was okay for linear direction equation, for example, to keep this time step constant. It is known, it turns out that for gas dynamics, that's not good. That's not a good idea. So usually the tau is tau n, and it can be different. So if it's the distance between Tn and Tn plus 1, different time layers. But for the evaluation from Tn plus 1 to Tn plus 2, the time step can be different. So you may know it from the numerical solution of ordinary differential equation. The situation just the same. So it's normal to have the different time steps during the process of numerical integration, depending on the behavior of your solution. So if you have very fast process, fast changing of your parameters, the time step should be lower. And quite contrary, if you have a slow process, you can increase the time step of your simulation. So the first question, how to compute this time step, Tn, and the second question is about boundaries. So suppose that m equals 1 and so on and so forth, n. So the numbers m from 1 to n, they correspond to inner cells. So they're inside our tube, they're inside our computational domain. So everything starts with m equals 1. So if you consider this the first cell, for example, m equals 1, it means that this is the physical boundary of our computational domain. But how can we compute this f1 minus 1/2 m f1/2? So this is the boundary, physical boundary. We do not have gas here, we do not have cells here. How can we compute this numerical flux? Or quite contrary, suppose that m equals to n, and this is the last. So imagine that this is the last cell of our boundary, and so this is the physical boundary, and we don't have cells here. So how can we compute this numerical flux? So how to impose and implement boundary conditions in simulations? So it turns out that although they understand the behavior, how to construct the Riemann solver, the usage of this solver in software, in code, is not straightforward problem. So you should solve some issues how to do that. So we are going to discuss these problems: how to choose this time step tau n, and how to implement impose boundary conditions. Actually, these topics are of great interest, in importance, and in fact, the quality of your boundary conditions and their numerical implementation, it totally affects totally defines your numerical result, especially in some Sony case. Let's start with the time step. So first of all, I'd like to remind you what do we have for the linear direction equation. So we discussed that there is so-called CFL stability condition. So I'd like to remind you. So we discussed previously the numerical scheme, current exoneration numerical scheme for the linear direction equation. It's an Alcuin scheme. So explicit Euler scheme for time derivative, and explicit backward derivative for special derivative, and it can be rewritten in the following form. We just can express un plus 1 and introduce the parameter sigma equals to lambda tau over h. This is the current number. And we discussed that this scheme can be interpreted as the linear interpolation at the nth time layer. So the numerical solution here is equal to the numerical solution at this point p, because this red line is the characteristic dx over dt equals lambda, but we do not know the solution here at this point p, and we try to find it as the linear interpolation of the solutions here and here. And so this formula states that our numerical solution here is just the linear interpolation on the nth time layer between the values here and here. And the weights are defined by these segments, these intervals, x1 and x2. And it's possible to show that actually this x1 is 1 minus sigma h, and x2 is just sigma h. And so this sigma is the physical meaning, or so just the meaning, is this weight for corresponding grid function, corresponding node. And we discussed that if characteristics is in between these 2 points, that everything should be okay. The scheme should be stable. But if, for example, these characteristics goes here, or here, or even here, but it's not possible because lambda is greater than 0 here, the scheme will be unstable. And it reflects the general statement called CFL stability condition, or Cohen-Friedrichs-Levy condition, or Levy, I don't know. The domain of dependence of the differential equation, that is point P, is the domain of dependence of differential equation, because the solution here is equal to the solution here. So the domain of dependence is only one point P. It should be entirely contained in the numerical domain of dependence of the discretized equations. That is the segment between 2 points, m minus 1n and mn. And so this segment is the numerical domain of dependence. And so the current exoneration scheme is stable if P lies between m minus 1n and mn. That is, sigma should be greater than 0 and less 1, 1. So this is the typical condition, stability condition. So what does that mean that sigma is less 1, 1? Sigma is lambda tau over h. It means that tau is less than h over lambda. And so the interpretation of the CFL stability condition is as follows. So during the integration time step tau, our signal should not propagate at the distance greater than our computational cell with the size h. That was for the linear case, and if you want to use this numerical scheme for the solution of linear direction equation, your time step should be less than this value. Otherwise, you're not able to use this scheme. You will see numerical instability. You will not obtain the result, the relevant result of your simulations. Let's apply the same idea for the Euler equations. But the problem here is that in Euler equations we do not have this constant lambda. So for linear direction equation, lambda is constant, and that's okay. But what should we do in case of Euler equations? So the idea is as follows. So the special discretization length. So usually, as in the same manner as for linear direction equation, h is some given parameter. So we want to compute with the necessary degree of discretization, trying to get the necessary accuracy of our results. So the special discretization length h is chosen on desired accuracy or available computing resources. Or we try to obtain the most accurate result as we can. That is why we can we can estimate the necessary amount of memory, and then we can choose the necessary spatial discretization. So we can think of h as of some given parameter. What remains to be determined is the size of our time step tau n. So again, let's use this condition. Let's try to obtain the generalization of this condition. For linear direction equation, we had tau equals sigma h over lambda. For the Euler equations, we have CFL parameter times h over s and max. So here, CCFL is a current or CFL coefficient or safety factor. So it's parameter between 0 and 1. It's the user-defined parameter. So it mimics that this situation is non-linear. And if you want to ensure, so if you want to add stability to our simulation, we should take this CCFL parameter smaller, for example, 0.5 or 0.3 or 0.1 or something like that. S and max is the largest wave speed present throughout the domain at time level n. So this is the sketch corresponding to the Godunov solver. So in Godunov solver, we have information about all these waves. We do not use them actually. So to compute the numerical flux, we need only parameters in necessary region in our solution. We do not need to compute actually the waves or the speed of this shock wave or the parameters of these characteristics of the expansion fan. But nevertheless, we can get this information if you use the Godunov method. So, what does it mean? This condition Tn equals CFL times h over Sn max. It means that the known wave present in the solution of all Riemann problems travels more than a distance h in time tau n. So we say that this wave should not travel more than a distance h in time tau n. If we would know all the speeds of these bounding characteristics, then we can take CFL number equals to 1. So it's the most accurate result. But the problem is that maybe we do not use the Godunov solver. So maybe we use some approximate Riemann solver, and maybe we do not know the information about all these waves. For the time-dependent one-dimensional Euler equations, a reliable choice is still the best result. If we know all these wave structures, we can take Sn max as maximum for all cells speed of left and right waves, where Sl and Sr are the wave speeds of all left and right nonlinear waves present in the solution of the Riemann problem. So, for example, if you know all these structures, we know the speed of this wave and the speed of this wave, the speed of this wave and the speed of this wave, and we can compute the maximum value for all of this all these waves and compute this value. This will be the time step. On the next time step, so we will have another set of Riemann problems. We will solve them. We obtain another velocities and obtain another time step and so on. So that's the idea. Yes, so they call that this Riemann problem generates three waves. The fastest are nonlinear waves such as shock waves and refractions. For refraction waves, one selects the speed of the head. So we introduced, so this is the head of a refraction wave, and this is the tail of a refraction wave. This is the head of a refraction wave, this is the tail of a refraction wave. So we should take the head and the speed of shock wave. But what if we do not have the information on these waves? For example, if we use current exonerized numerical flux. So we do not build these states, we just obtain directly the formula of the numerical flux. If an approximate Riemann solver is used, the speeds of the left and right waves are not available. A popular alternative for estimating S and max is the following value. For each computational cell, we compute the model of velocity plus c, where c is the speed of sound. You do not need to know all these velocities of shock waves or refraction waves and so on. It's very simple. And actually, it's really used in practice. And however, it's not difficult to see, however, that this formula can lead to underestimate of S and max. So, for instance, if we have the gas at rest, for example, Vmn equals 0, the estimation for S and max is based only on the speed of sound. So S and max can be too low, and it leads to that our time step computed using this formula will be too big. That is why we need this CCFL parameter. So if you want to use this formula, then we should apply safety factor such as 0.1 or 0.2 or something like that. So if you would apply the exact approach, maybe we can use CFL parameter equals to 0.9. And if you use this approximate, so anyway, it's a reasonable approximation for this S and max. But actually, we should apply the safety factor or CFL number. A possible way of correcting this is by choosing the CFL coefficient cautiously. So if S and max is known reliably, then we can choose so CFL just 1, or in practice 0.9. If there are uncertainties in the estimate for S and max, a more conservative choice of safety factor is advised. Okay, so that's the idea. How can we choose the time step? And actually, this approach is used in the program, and I will show to you where these formulas are implemented. So at the first part of lecture, I'm trying to explain to you all the features that you will see at the second part of the lecture in code. And so that's the main idea. Okay, let's move to boundary conditions. So we discussed how to choose the time step. So the main idea is the time step should be chosen dynamically. It's not a constant value, so we should choose it based on the current solution that we obtained at the nth time layer. So now the boundary layer, boundary conditions. So we'll consider two types of boundaries. I will explain to you how to construct boundary conditions for two cases. For the case of a solid wall and so-called far-field boundaries. So they are, not the simplest, but the most widespread, and so usually you need them. So if you want to compute internal flows in tubes or tanks or I don't know where, always you have walls, and so you need to know how to implement the solid wall boundary condition. If you compute the external flows, you have some boundaries. For example, if you compute the flow around a wing or some profile, you have some parameters at the infinity, and you should know how to implement these far-field boundaries. So that is why these two types of boundary conditions are, the most widespread. Although there are other types of boundary conditions. Solid boundaries are also known as surface, wall, rigid, or impermeable boundaries, or non-penetrating boundaries. So naturally enough, solid boundaries occur at the surfaces of solid objects. That's obvious. And actually, these solid objects can move or non-move, so we'll discuss only the basic case of non-moving objects. Far-field boundaries are also known as open boundaries, artificial boundaries, permeable or remote boundaries, and they limit the computational domain to reasonable finite size. So the problem is that it would be great not to have this artificial. Why artificial? Because in reality we don't have this boundary. So we have some space, but we are not able to compute our problem in unconfined space at all. We should impose the boundary, and we should define the boundary conditions. The true boundaries may be extremely far away, or even infinitely far away, at least conceptually. In general, when the physical domain is very large or infinite, then the farther away the numerical far-field boundary is the more accurate, but also the more costly the numerical approximation will be. Far-field boundaries are divided into inflow boundaries, where fluid enters the computational domain, and outflow boundaries. So we also discussed the inflow and outflow. Solid boundaries are purely physical. So if you have only solid walls, so that's great. So in my simulations, I try to have solid boundaries, right? Because they're physical, so they're just walls. Quite contrary, the far-field boundaries are maybe not purely, but almost purely numerical, because in reality you do not have physical parameters at these boundaries. You just imagine and set them. Solid boundaries, they reflect existing waves. At the same time, far-field boundaries, they both absorb existing waves and emit new ones. So far-field boundaries are dangerous because there is an interaction of your waves from your computational domain with these boundaries. And the problem is that usually you're not able to predict what will happen when the different waves from inside of your computational domain will interact with your far-field boundaries. And that's the problem. There are two basic strategies how to implement the boundary conditions in programs. So I enjoy this book of Lenny because he provides very straightforward statements on the relative computations. So because numerical boundary treatments are so much of an art, even more than that, the interior. So actually, the boundary conditions is a sort of art, and actually, as I told, the result that you obtain, especially for subsonic case, they're defined by your boundaries. And for example, if you impose boundary conditions somewhere here, nobody knows what will happen if you add some more length of your computational domain and impose this condition in 1 meter, for example. For sure, you will somehow change your numerical results, and so that's a problem. And there is often no way to predict in advance when the numerical results will be especially sensitive to boundary treatments, and if so, which boundary treatment will yield the best results. Some computer codes include several different far-field boundary treatments. So, from physical point of view, for example, you want to establish some pressure. So you say, okay, this boundary is far from our place we are going to study our flow. Let's set just pressure at the infinity. But it's possible to do it in different manner. And in your code, you have different implementation of the same physical boundary condition. And if you're just a user, maybe you just have no idea of difference for these different implementations of boundary condition. Then if the code exhibits mysterious instability or a drop of accuracy or failure to converge, the user can easily switch to different far-field boundary treatments, sometimes with dramatic improvements, right? And so that's a typical process of the numerical study of a problem using the black box software. When you just try to use different types of boundary conditions in hope that for one of them you will get the convergence and reasonable results. That is why we still need to develop our own softwares, not to be in this situation. Anyway, there are two basic types of grids depending on the alignment between the grid and the boundaries. So this is type 1, when the boundary is aligned with the cell edge. And so type 1 grids are the most common type of grid for finite-volume methods. So we, within the scope of our course, we try to use finite-volume methods. And so this is our case. So we have computational cells, and for the computational cell number 1, m equals 1, the left boundary of this computational cell corresponds to physical boundary. For example, a wall or some boundary that we would like to name far field boundary or open boundary or something like that. Another option is the type 2 grids. The boundary is aligned with the cell center. Type 2 grids are the most common type of grid for finite different methods. Another approach is to say, okay, we should know we should have some boundary condition. So it means that we should know exactly the parameters at the boundary. Let's consider the last cell as some cut cell or small cell or something unusual. But we should know parameters here, and we will use some other approach how to solve how to resolve this situation. This is usually used for finite different methods, and we will not use this. We will not use this option. What is the main difference between two strategies? So near boundaries of either sort, numerical methods usually require values from outside the computational domain. There are two ways, again, of dealing with this problem. Either change the method or change the computational domain. So you will either change the method. It means that for this computational cell, everything will be the same. But when it comes to the boundary, you should somehow resolve this situation. And so you will change your numerical method. So the numerical method will not be uniform throughout the computational domain. There is another choice. Another choice, we want to keep the numerical method just the same. On this way, we need to compute this computational cell. It means that we should introduce so-called ghost cell here, define somehow parameters here, and then compute the numerical flux through this boundary, physical boundary, in the same manner as we would do it for this boundary, and so on. So we should introduce the ghost cell, define parameters in this cell, and use our general finite volume method. So in other words, the interior method may be changed to a special boundary method with completely or partially biased away from the boundary. Alternatively, the computational domain may be changed by introducing cells outside of the computational domain called ghost cells. Ghost cells or fixture cells, so cells that are not real. And we introduce them to keep the same same structure of our numerical method. Either approach, a combination of numerical boundary treatment. These activities are called boundary treatment. Note the distinction between the numerical boundary treatments and physical boundary conditions. So, once again, from physical point of view, it should be a solid wall here. But from numerical point of view, you can implement this boundary condition in different ways, depending on your scheme, depending on the desired accuracy of the numerical method, the stability of numerical method, and so on and so forth. So there can be different numerical implementations, different numerical boundary treatments for the same physical boundary condition. This is just an example, right? Boundary conditions, which include the non-penetrating boundary condition, and in viscous flows, mostly boundary conditions, only partially specified boundary flows. For example, if we solve I think maybe one of the last lectures will be about the numerical solution of Navier-Stokes equations. So when you solve Navier-Stokes equations, the typical boundary solution is so-called no-slip boundary solution. Right? No slip. No slip means that V equals 0. So just the velocity of gas should equal 0 on the surface. But you have also pressure, density, or temperature, and so on and so forth. So it means that so the physical boundary condition does not define all the rest properties of the flow. And boundary treatments reconstruct and model the flow properties at the boundary using both boundary conditions and interior flow. Unfortunately, many sources use the term boundary treatments and the boundary conditions synonymously. Okay. So here the most important idea is that so the possible use different numerical implementation of your physical boundary conditions. We will follow the idea of ghost cells. Let's discuss some main results of the theory of how to impose boundary conditions for the inlet and outlet, inflow and outflow boundary conditions. I told so when we constructed the we tried to find self-similar solutions of Euler equations and simple waves. I told to you that this form can be useful for implementation of boundary conditions. Here I'd like to explain that idea. So this is a review of previous lecture, characteristic analysis of Euler equations. At that lecture we were interested in simple waves because we tried to construct Riemann problem solution. We discussed that there is a conservation form of Euler equations in primitive variables. Then it's possible to diagonalize matrix A, and so use the same procedure, multiply by omega r to the left, both sides, and on this way we can obtain Euler equations in this form. So Euler equations in characteristic form means that we have, at each point we have three characteristics, C0, C plus, and C minus. And the disturbances in the form of Riemann invariance, V sub 0, V plus, and V minus, they propagate along these characteristics. The characteristic dx over dt equals V is called entropy wave, and dx over dt equals V plus minus C, they're called acoustic waves. That's it. So this is the characteristic form of Euler equations. So we know that for each point A we have these waves, and this is domain of influence, and this is the domain of dependence. Let's apply this knowledge here. So suppose we have our computational domain, x equals x0, x equals to x1. So this is the left boundary, and this is the right boundary. And suppose, for example, that the velocity of gas is greater than 0, u is greater than 0. And so this boundary is inflow boundary condition, and this one is outflow boundary condition. So if we would be able to simulate, for example, the whole shock tube or the whole duct of our engine to consider all walls, so that would be no problem. But actually the problem is that usually we are not able to do that. That is why we need to compute only part of our device, and because of that we should somehow define the inflow conditions and outflow conditions. So consider the inlet plane x equals 0, and outlet plane x equals x1, and points p0 and p1 at a given time at these boundaries. So even the number of boundary conditions is not an obvious question. The number of boundary conditions to be imposed will depend on the way the information transported along the characteristics interacts with boundaries. So let's plot the characteristics line here at point p sub 0. We can plot characteristics C0, C plus, and C minus. I mean this one. C0, C plus, and C minus. And you can see that the slope of each characteristic depends on the local speed of gas, V, V plus C, and V minus C. So if V is greater than 0, we have the positive slope for this characteristic and this characteristic. And the slope of this characteristic depends on the relationship between V and C. If V is greater than C, we have again the positive slope for the last characteristic. But if V is less than C, we have characteristic with another slope, negative. So what does it mean? At the inlet point P sub 0, the characteristics C plus and C minus have slopes V plus C and V, which are always positive for a flow in the positive x direction. So we just discussed it. That's obvious. Therefore, they will always carry information from the boundaries towards the inside of the domain. So it means that for C plus and C minus, C plus and C0 characteristics, they comes from outside the domain, and they bring some information from outside. So it means that we should impose some physically relevant boundary conditions depending on your statement of the problem for these two characteristics anyway. So if you have the inlet and the u is greater than 0, then you should impose two boundary conditions along C plus and C0 characteristics. This requires the values of the transported quantities to be known at P0. The third characteristic, C minus, has a slope whose sign depends on the inlet Mach number. For the supersonic inlet flow condition, C minus will have a positive slope. So if V is greater than C, supersonic inflow, it's a positive slope, but a negative slope at subsonic inlet condition. So if you have subsonic inlet, the C minus is less than 0. So you can see that this is a principal difference. It means that if for this case, for C minus characteristics, you do not impose boundary condition, because this information comes from interior of the domain. It means that, but it doesn't mean that you should do nothing with that. It means that you should use so-called numerical boundary condition. You should treat the situation and analyze the propagation of V minus Riemann invariant along this C minus characteristic. So we discussed that the behavior of characteristics at the inlet boundary depends on the relationship between gas velocity and speed of sound. So in the first case, when the velocity, so the flow is supersonic, the information from the inlet surface enters the domain and the corresponding boundary conditions has to be imposed. So for the supersonic inlet, you should define finally this results in that for the supersonic inlet, you should impose all variables. I mean velocity, pressure, and density. So if you have supersonic inlet, you should define all these parameters. On the other hand, at subsonic inlet condition, information from inside the domain reaches the boundary along C minus, and no boundary condition associated with C minus is allowed to be fixed arbitrarily. So it means that if you have subsonic inlet, you should construct your inlet boundary condition in a special manner. For example, so there are popular types of physical boundary condition for the subsonic inlet. If you set stagnation temperature and stagnation pressure, or stagnation temperature and mass flow rate, and other options are possible. So I'm not going to describe in detail how to do that, but the idea is that depending on the flow regime, on the velocity of your flow, the implementation of boundary condition can be totally different. Similar consideration can be made at the outlet. So here situation is even more interesting. Two characteristics, C0 and C+, always reach the outlet from inside the domain, because the slope is positive, V and V plus C. And therefore they determine 2 of 3 independent characteristic variables in the outlet plane from the behavior of the interior flow. The third condition is dependent on the outlet flow Mach number. For supersonic outlet velocity, no boundary condition is to be imposed, while at subsonic outlet velocity, one boundary condition is to be fixed at the outlet section. Because for supersonic outlet, the slope of the third characteristic is also positive, and it means that all characteristics comes to the right boundary from the interior of our boundary. It means that for supersonic outlet, you do not need to impose any boundary condition. That's maybe confusing for students, for PhD students, that actually if you have supersonic outlet, you do not need to impose anything. But the problem is that the reason for this confusion is that if you solve the problem numerically, you for sure should impose something at your ghost cell at the right boundary. And although from a mathematically rigorous consideration, you do not need to apply any boundary conditions, anyway, you should set something in your ghost cell. But actually, the numerical implementation should work in such a manner that it should not affect the result, the solution here in your ghost cell for the case of supersonic outlet. But as for subsonic outlet, we have one characteristic that comes from outside of our domain, and it means that we need to specify something. And for example, the popular statement is the statement with certain static pressure. For example, and other conditions can be obtained from consideration of relationships for C minus and C0 characteristics. And this is the brief summary. So the subsonic, supersonic inlet outlet. For subsonic inlet, you need to impose 2 conditions for V0 and V plus. And for subsonic outlet, you should impose 1 condition for V minus. For supersonic inlet, you should impose 3 conditions. And for supersonic outlet, you should not impose any conditions at all. And you should make a distinction. You should realize the difference between physical conditions and numerical boundary conditions. So the physical conditions to be imposed are the entropy and the values of the characteristics of Riemann variables. This is not a very practical. So the problem is also the following. So all this is discussed in terms of characteristic variables and Riemann invariance, this one. And they can be analytically computed and so on, but for real guys, the problem is that if you're an engineer and if you try to solve some real problem, you think in terms of velocities, pressures, temperatures, densities, not in terms of these strange, complexes. And there should be some procedure how to, transfer, how to move from physical variables to these parameters for which the boundary conditions should be implemented. So anyway, at the level of numerical method, you should work with this Riemann invariance, but they also should be connected with the real physical statements, real physical parameters from your problem. And here, instead, the conditions that are fixed in practical situations in experimental setups are velocities and pressures, usually. And therefore, the characteristic information might have to be defined in approximate or some iteration procedure. So the red characteristics correspond to physical conditions. So here, from some physical consideration depending on the problem, you should realize the conditions for these red characteristics here. And for green characteristics, on the other hand, the numerical schemes generally require the values of all the variables at the boundaries. So what does it mean? So I try to explain to you that you do not need conditions here. In your simulations, for sure, you should have some conditions, but they are not physical, because from physical point of view, for supersonic outlet, you do not need any conditions. But from numerical point of view, you should use some, numerical boundary conditions. On the other hand, the numerical schemes generally require the values of all the variables at the boundaries. Hence, additional conditions on numerical origin will have to be added to the physical conditions in order to define completely the numerical problem. These conditions, called the numerical boundary conditions, correspond to the boundary variables defined by the inner flow inside your domain. And say they should reflect in some way this information which is dependent on the yet unknown internal flow conditions. And so that's it. So we discussed that the situation at the inlet and outlet can be different depending on the velocity of the flow and the difference between physical conditions and numerical conditions. And also we discussed the different ways how can we impose boundary conditions. So either using change of method or changing the computational domain. That's only a very introduction to the theory of implementation of boundary methods. And the most problem is that very often all these things you don't see it if you use some software. For example, you know that no physical boundary conditions are required here. And for example, if you try to simulate some supersonic problem using Fluent or NCCFX, maybe sometimes you will see that you need to set some pressure. And so the question is, so what does it mean? So for example, from physical point of view, you know that if you have supersonic flow in your domain, you do not need any physical boundary conditions. But for example, software can require you set some pressure. And that's also a very confusing thing. And once again, that is why we should understand all this theory. Okay, now closer to our program. So we discussed some general theory. Let's discuss how can we implement our. So I told you that in the program that I would like to explain to you, we should have two types. I'm going to explain to you how to implement two types of boundary conditions. The first one is a solid wall. So suppose we have these two internal cells, number 1 and number 2, and this should be a solid wall. And then we should introduce some ghost cell, number 0, and the idea is that we should set parameters in this ghost cell in such a manner that the solution of the Riemann problem for these two cells would provide the solid wall. What does it mean, solid wall? It means that there is no flow through this wall. It means that the velocity here at this point should equal 0. How can we reach that? It is known that, for example, if you have parameters, primitive variables vector W1 here rho Vp. The correct implementation of solid wall boundary condition is to set parameters in the ghost cell as rho1 minus V1 P1. So we should take the same density and pressure and take the velocity with the opposite sign. Why is it so? It's possible to see from the analysis of PV diagrams. So I'd like to remind you that we used these diagrams when we discussed the solution of the Riemann problem. In fact, here we also have this problem. Suppose that, for example, V here in this neighbor, so in the first inner cell of our computational domain is greater than 0, and there is some pressure P1. So this corresponds to point 1 at the PV diagram. So this point 1 corresponds to the state here. And we can plot all possible states for this gas in this cell if a shock wave or a refraction wave passes through this gas. So this is for shock wave, this is for refraction wave. And let's put the point corresponding to point 0. Here, this point has, so the gas here has the same pressure and velocity with opposite sign. It means that it will be at the same level P1, but with velocity minus V1 here. And then we also can put all possible states here. And so these two curves are just symmetrically relative to this axis V equals 0. It means that the intersection point will here, so this point corresponds to the contact discontinuity. It will correspond to V star equals 0 and some P star. But anyway, so if you use, and it means that if you use any consistent relevant numerical flux, anyway, it will give you the result that V star equals 0. So you can use the same solver, Godunov solver, current axonomy solver, HLL solver, HLLC solver, doesn't matter. You use it between each two cells and also between these cells and this cell. And for sure, it will give you 0 velocity. It means that it will wall. And the pressure will depend on your numerical flux. So you will get either an exact solution if you use Godunov solver or some approximation to this P star using your numerical method. But anyway, this is the way how can you get the solid wall boundary condition using both cell method. The same thing if V1 is negative. So suppose that V1 is negative. So yes, and this point corresponds to refraction wave. So what does it mean that V1 is greater than 0? It means that gas move outside the wall. And that's obvious that there should be some region of refraction between gas try to move outside the wall. So we get that the solution is on the paths corresponding to the refraction. Quite contrary, if V1 is less than 0, it means that gas moved towards the wall. It means that we should have some shock wave. So we plot all possible states for gas 1, all possible states for gas 2, and so the intersection point will be here for these two red paths, P star, and again, because these curves are just symmetrical, V star equals 0, and we get some P star greater than P1. And again, depending on the numerical method, you will compute this numerical flux, you will get some approximation to this P star. So more accurate, less accurate, does not matter. It depends on your. So we do not discuss multi-dimensional case. We do not discuss here high order scheme. So this is just first order scheme. But the most important to understand the basic things. Okay, so if you want to have a solid wall, you should impose this condition. You should self the parameters like this one in your goal cell. And if you want to have an open boundary, it's not actually. No, it's open boundary, but it's not non-reflecting boundary. So the simplest way how to set open boundary is to use just the same parameters in the ghost cell. So suppose we have parameters ρ1, v1, and p1 here, then you can set just the same parameters here in the ghost cell. And actually there is a bit confusing statement from Toro's book regarding this case. He writes that transmissive or transparent boundaries arise from the need to define finite or sufficient small computational domains. The corresponding boundary conditions are a numerical attempt to produce boundaries that allow the passage of waves without any effects of them. This idea, so this data produces a trivial Riemann problem. No wave of finite strength is produced at the boundary that may affect the flow inside the domain. So it looks like if you choose this very simple method for ghost Gauss cell parameters, you will not have any flows inside the domain. And formally, if you consider only this Riemann problem, that's true. Because if you use the same parameters, the start state is just the same as 0 and 1, and you will have just the same parameters. But the problem is that for sure that this type of your boundary condition will reflect your disturbances somehow in your domain. Because here, for the subsonic case, it doesn't take into account all this theory. And so this open boundary works well only in two cases. The first case is when all the parameters are constant here. So it works for Riemann problem, and for Riemann problem up to the instance when disturbances reach the boundary. Or it works well for supersonic outflow, because you do not need any boundary conditions at all. So this is the simplest possible way how to implement open boundary, but this open boundary actually is not open at all. If you have subsonic disturbances, they will interact with this Gauss cell and produce you some unpredictable actually disturbances. But anyway, for our purposes, let's just know, for example, if you want to solve Riemann problems up to the instance when disturbances reach the boundaries, that's okay. You can use this form of open boundary. Okay, so we discussed almost, okay. So the last theoretical part before discussion, the implementation in code, I have already shown to you that I told that we are going to use this numerical flux, and this numerical flux is based on these matrices omega r, lambda, omega l. This is the matrices for Jacobian matrix in case of conservative variables vector, and we need to know these matrices. And we discussed them when we analyzed the characteristic form of Euler equations, and I told to you how to compute these elements, and actually I provided a bit more detailed explanation one more time. So suppose we have this conservative, so one more time for maybe more careful. So U is conservative variables vector, rho, V, E. Let's denote the components as U1, U2, and U3. F is flux vector, rho V squared plus P in the third term. F1, F2, F3. F3. We need to compute the partial derivatives dfi over dug j. For example, consider the first non-trivial component df2 over du1. It means that we should take the derivative of this guy, rho v squared p, over u1. u1 is rho, d rho. So d over d rho v squared plus p. But p is not an independent variable. It is a function of the independent variables. So p is a function of rho and epsilon, where epsilon is internal energy. But epsilon is also not an independent variable here. So we can consider the expression for E and express epsilon from here. And now epsilon is function of rho, v, and E, our independent variables. And so P is a complex function of rho and internal energy here. So if we choose such variables, P and E, they are functions of independent variables. And then, okay, we can write here that just rewrite. So d over d rho of rho v squared plus p of rho and epsilon. Then there is a small, trick. We multiply the numerator and denominator by rho v squared over rho, and now we see that rho v and rho are independent variables, and it's very easy to compute this derivative. And the question is how to compute this derivative. D over d rho of p as function of rho and epsilon. So just keep it here, because this is the derivative of this term. D over d rho of 1 rho is minus rho squared. This is independent variable, we just keep it. And now we should compute the derivative of this function of rho. And this is a complex function of rho. So first of all, we should compute the dp over d rho under the constant epsilon is for the first argument, and then we should compute dp over the epsilon and the epsilon over the rho for the second component. Just like in mathematical analysis, the derivative of a complex function. And then we take into account the epsilon is a function of rho v, and e, and so on. And then very simple, mathematics. And finally, we get this expression. And again, these formulas are valid for general equation of state. So we can actually put here, for example, dp over d epsilon is rho gamma minus 1 and so on, but we don't do that. So we keep here all the parameters as in general case. Okay, so now details of implementation. This will be a program in C, actually written for Microsoft Visual Studio. And as I told also, I prefer not to use these, all objects and so on. For the computation of, typical gas dynamical programs, the procedural approach is valid. Actually, I can also share this code for educational purposes, not a problem. And there are several functions. The typical structure is as follows. So this file main.cc, which contains the main loops for time and spatial coordinate integration, file with all the constants, file responsible for construction of the computational grid, implementation of numerical flux, CIR, implementation of currents on with numerical flux, a lot of different utility functions to compute the speed of sound, conversion of conservative variables to primitive variables, and so on, and input-output. And as a result, the program computes the spatial distributions of density, velocity, pressure, and internal energy at a specified time instant. So we want to compute the solution of SOT's test here, and I'd like to show you how can it be done. So first step, and we build the computational mesh. So actually it's just a uniform mesh, so we define the coordinates of our cells and the boundaries of our computational cells. Then we should initialize the solution. So in simplest possible case, the left part of our computational domain, we set parameters in the driver section, and to the right the parameters in the driven section. An important thing is that in program it's better to use conservative variable vectors, because our numerical scheme is written in terms of conservative variables vector u. That is why it's better not to have vector for pressure, velocity, and density. It's better to have vector of rho, v, and e. But it's more difficult to debug this program, because if you check the components of this vector, that's a bit difficult to understand if everything is okay. But nevertheless, yeah. So you can set the initial data in terms of density, velocity, and pressure. But after that, you should convert the non-conservative variables to conservative variables, because the numerical scheme is written in the terms of conservative variables. Yeah, so this is the function how to build the grid, so just uniform grid. And this is the main time loop. So we do time steps and move from one time layer to the next time layer, compute the time step according to the method I explained to you. And in this time loop, we have a cell loop. So we should check all our computational cells. As for constants, we have two types possible boundary conditions. So we discussed the wall boundary condition and far field boundary condition. In the program, they are called wall boundary condition and free boundary condition. And so this is the statement of the problem. It corresponds to the SOT problem. Parameters to the left of discontinuity, parameters to the right of discontinuity, the final time instant. And so to the left and to the right, we would like to install wall boundary condition. So suppose we consider the propagation of a shock wave in a shock tube, and I will also show you how the reflection of the shock wave from the wall will look like. Okay. Okay. Yeah. So this is again. I'd like to remind you that this test is taken from the paper of SOT. We have already discussed it. Not to lose this time. One of the functions that usually exists in each solver is the function how to how to transform from conservative variable vector to non-conservative or primitive variable vector. So we have conservative variable vector and primitive variable vector. And so this is a very simple function how to transfer from U to W and from W to U. This is a straightforward procedure, but it's better not to use these formulas each time when you need to do that. It's better to have this function to do that. Okay, so this is the main cell loop. How our boundary conditions are implemented. So the structure is as follows. So we take one computational cell and we need to compute the numerical flux through the right and through the left boundary of our computational cell. If our computational cell is not the first one, we compute the numerical flux based on the parameters to the left cell, into the current cell, and this will be the left flux. If the computational cell is not the last one, we use our current cell, the right cell, and compute the right flux. But if our computational cell is the first one, and in C, everything starts with 0, so E equals 0 corresponds to the first computational cell. Then we call the function boundary and compute the bound V. Bound V are the parameters in the goal cell. And so we tell the type of boundary condition to the function boundary. And after we get the bound V, so the parameters in the goal cell, we call just the same calc flux function as previously, but instead of parameters to the left cell, we use parameters in the boundary cell. So the logic is very simple and straightforward. Or quite contrary, if the cell is the last one, we call the function boundary. It defines parameters in the goal cell to the right, corresponding to necessary type of your boundary, and then compute the flux using parameters in the current cell and parameters in the neighboring ghost cell. And that's it. And you obtain right flux. And this is the formula of the finite-volume method. It's obvious. And that's it. And at the end of this cycle, we just should store our new conservative variables vector in upref. That's it. This is function calc time step dt, which is called at the beginning of this main time loop. It implements this approach that we discussed at the first part of our lecture. Yeah, it's even a bit complex, like in Toro book. During the first n1 time steps, we use one safety factor just for to initiate the simulations, and after n1 time steps, we use CFL number, which is a bit bigger, right? Here maybe we use just the same values. Yeah, here they're just the same, 0.2. Doesn't matter. Function to compute the speed of sound. For sure, it's very simple here, and maybe there is no need to use the separate function, square root of gamma p over rho. But for the case of, for example, more complex equation of state or something like that, so it's better to have a separate function to compute the speed of sound. And okay, so this is a general structure. So of the of the cycle of the cells. Now we should check the calc flux function. So this is a very general framework. So you can use Godunov flux or HLLC flux or Kronecker-Sonneries flux. So this part will be the same. The only difference now is how to compute this numerical flux. And as I told, usually people in their programs have a set of numerical fluxes. Because in different situations, in different types of flows, different methods works better. Okay, so this is the Kronecker-Sonneries flux, And the structure, yes, the input parameters are parameters to the left, the conservative variables to the left, to the right, and finally the result should be the flux. And here this formula is implemented. So this is the Fm plus 1. Here we compute this matrix, and this is the formula for the flux. And so we need to have these matrices here, right? Here. So here this multiplication of matrices, and for that we should have some mathematical functions, how to multiply these matrices. Yeah, and so we have a function calc omega. It's the omega r, and omega inverse is omega r. And you can just check that here in this function, just the formulas for these matrices are implemented. That's it. So on previous slides, I've provided these matrices. So as you can see, I try to write the code in a clear manner. Yes, and by the way, it's necessary to say that you can easily make the program faster by a factor of 2. Why? Because this is only teaching example. How does it work? So we take one computational cell and compute the numerical flux through the left and through the right boundary. Then we take another computational cell and compute the numerical flux through the left and through the right boundary. But the beautiful property of the finite-volume method is that this numerical right flux for the cell M is the same as the left flux with the opposite sign for the next cell. So it means that for sure, if you want to do research, not just study how to do that, you should rewrite this program and have a cell and have a cycle not over computational cells, but over computational edges. And then you need to compute flux only one time. And then you should collect in an array all these numerical fluxes. And then at the end, you should just add this flux with different signs to neighboring cells. And on this way, so the most demanding procedure, the computational costs are due to computation of flux. And so here, so you can see it's very most frequently used function. And so generally speaking, this calc flux function should be very, well written. And for sure, you should not use them. You should not call this function twice for each computational cell. You should call it only one time for each edge of your between your computational cells. So, but anyway, I think that in such a manner the program is much more is clear, and our main goal is just to understand how to do that in principle. This is the so this function boundary which compute the parameters in the ghost cell. Okay, it's very simple. So if the boundary type is wall, we implement just this approach for wall. We keep the density and pressure and change the sign of the velocity. If we have the free boundary condition, far field boundary condition, we just copy parameters from the cell, from the first or from the last cell of our computational domain, and define the parameters in our ghost cell. That's it. Yeah. And so the results. The sort problem. Parameters to the left are 1, 0, 1. To the right, 0.1, 0, 0.125. And the time instance is 0.2. And we discussed how to build this exact solution, a red curve. And the blue markers, they correspond to the numerical solution obtained using this program. And we can analyze both of them simultaneously and discuss the general features. So this is a shock wave. So you can see that in simulation we have smearing of the shock wave, and the method that we use is first order method. So we will have 2 lectures about the development of high order methods. But as for low order methods, first order method, we have the smearing into 8 or 9 computational cells, but actually this is not a constant. So this 8 or 9 depends on the problem. So if you compute for a longer time, or if you change the parameters of the Riemann problem, we can get totally another number of smearing of your shock wave. It's not important. Important the correlation between the number of smearing of your shock wave and contact discontinuity. So specifically in this test, you have a smearing for into 8 or 9 computational cells for your shock wave. But the contact surface is smeared into about 15 cells. So it's much more smeared structure. And the contact surface suffer from shock capture methods at most. This is the contact surface, and this is the refraction wave, continuous solution. And people usually, so if you open papers, so where people try to compute this test, they always are proud if they have only 1 or 2 points here and a couple of points here, and they also analyze this point. So this is the head of the refraction wave, and you can see also there's a big error here, and people also try to get better results in this region. Actually, we discussed already that although for example, for the Godunov method, here you will see the entropy glitch, and for current sonoris, the solution here is almost excellent. And this is although actually no, you also here for the velocity some rise, so this should be a constant. And this is velocity, and we do not see the jump of velocity across the contact surface, but this is a shock wave, a refraction wave, and we also discussed that in the refraction wave, the velocity is linear. It follows from analysis of a simple wave, and so that's a typical property of this simple wave. Head of a refraction wave and tail of a refraction wave. And the distributions for pressure. And again, the pressure at the contact surface is continuous. Actually, at different lectures, when we discussed, for example, shock waves, I have shown you these results, and the lecture for HLLC method and so on. So we have already discussed several times. So that such sort of pictures, I think it's useful for you to to be familiar with this typical solutions. And this time instant 0.2 correspond to a moment when the shock wave had not reached this boundary, and the head of a refraction wave also. That is why here and here we have undisturbed parameters. So this is still self-similar solution. But today we discussed the boundary conditions. Actually, here the wall boundary condition is imposed, and here also wall boundary condition is imposed. What will happen if we continue simulation? So this shock wave, it propagates to the right, and it should interact with the right boundary. And so the last slide, how this result will look like. So this is the refraction wave and the head of refraction wave. So it propagates here and interacts with the left boundary, and the shock wave propagates to the right and interact with the right boundary. And you can see the reflection. So this is the contact surface, the refraction wave, and now you don't have this. You do not see this shock wave. It interacted with the wall, and you obtain the reflected shock wave. So it's only started the formation, and it will move towards with the formation of parameters behind the reflected shock wave. And it's also known the exact solution for this problem. Actually, even here it's possible to build the exact solution. Maybe next time, at the next courses, I will do that. But this is the example of how the solid wall boundary condition works. It works in such a manner. So you have the reflection of the shock wave.